presenting. Is it visible now?
Yes, sir.
Okay. So I will start from where we left yesterday. Chapman, as we are now very clear or clearly know that Chapman only introduced two terms, production and loss, but physical mechanism in the ionosphere is also controlled by transport. That is for the continuity equation. Along with continuity equation, we also need the momentum equation. That means because the ionosphere is not static, it is a dynamic medium, so you need the momentum equations to also take part within the system, means when you discuss or when you study the ionosphere, plus the energy. Energy because you are receiving energy from the sun and you are also losing energy due to radiation and other factors. So, means by conduction and convection. So, all these three, it is a set of equations which will govern, or set of the processes, I won't say equation, set of processes which governs the dynamics of the ionosphere at any given time. Now, what we are looking at right now is the vertical distribution of the ions and electrons within the ionosphere. So we came from the bottom, we had discussed the D layer, we also have discussed the E and F1. Now, we are going still higher up, and where maximum ionization takes place, because the vertical profiles, all of us know that it is the F2 peak, which has got the maximum amount of ionization. So, why that F2 peak happens? Earlier, as we have said, if we go by that equation, that it will continue, it should continue to rise, but it doesn't continue to rise. So now we know why it doesn't continue to rise. When we consider this transport or movement of ionization from one place to another, in this particular, right now, we will be considering, we will forget about production and loss. We will concentrate on the movement. For the continuity equation, we are not bringing in momentum and the energy equations, energy balance equations. We are looking at the continuity equation only. So continuity equation, the third term, the transport, is due to diffusion. Okay, we will consider that the movement of ionization is due to diffusion or vertical movement. Why vertical movement? Because the gradients in the ionosphere or in the atmosphere, if you consider the atmosphere as a whole, vertical gradients are very large. Vertical gradients because of the natural gas environment, natural temperature environment, and also because the ionosphere or ionized plasma resides within the atmosphere. So you have a large vertical gradient at any place over on Earth, over any place on Earth, you will get a large vertical gradient compared to the horizontal gradient. Within the ionosphere, we can consider the ionosphere to be horizontally stratified. That means horizontally more or less similar. Okay, equitable distribution. But vertically it is not. Vertically it is not because of gravity, because of the other factors. We know the atmosphere itself does not have equal distribution of all the atoms and molecules across the atmosphere. So because of that, what we get is a kind of 1:10 ratio of vertical gradient and horizontal gradient. Okay, so if the vertical gradient is say within of 100 kilometer, then your horizontal gradient may be 1000 kilometer or more. it is like that. That means one order of magnitude in across the horizon or horizontal direction. So you may neglect that movement. You may neglect that movement, and because the vertical gradient is large, the movement or diffusion will also be vertical, mostly vertical. So we can write the third term dn for the change in the continuity equation, number density of change in number density of electrons or ions with respect to time is divergence nv, where v is your velocity or divergence. So if we confine this to vertical movement only, then dn dt becomes equal to del h wn. What is w? Will come. Del h, because we are now looking at a height, not distance horizontally. It is the height, altitude. So del h wn. W is the drift velocity in the vertical direction. So we consider W to be the drift velocity in the vertical direction. N, of course, number density of electrons, and H is the height. So in the present case, in this case, this equation, if we are looking at this equation, we assume the vertical drift is due to diffusion only. The vertical drift is due to diffusion only. We are not considering other factors. It is a diffusion only. So W is equal to minus is because it is a loss term. So d by n del h. What is this d? This is the diffusion coefficient. This diffusion coefficient, if you have come across this diffusion coefficient earlier, I am not sure. Maybe you might have come across the diffusion coefficient. So we can write this diffusion coefficient d in its simple form as kt by mv. V is velocity. The other terms are kt and m is the mass. So in this particular case, if you look at this expression, this is similar to another expression which we have come across, h, the scale height, kt by mg. Z is replaced in this case by v, velocity. So kt by mv. So the diffusion coefficient will depend on temperature and the velocity. Okay, so velocity of diffusion, velocity at which the plasma is diffusing in the vertical direction, either upward or downward. So when the vertical motion is there, you cannot neglect the effect of gravity. Because if it is going upward, then gravity will try to pull it down. There will be a drag. If it is coming downward, then gravity will add to the motion or velocity. So gravitational force, the effect of gravitational force must be included in the process of vertical movement. When something is moving vertically, when anything is moving vertically over the surface of the earth, gravity will play a part. So we cannot neglect that, and we are now bringing in that gravity term. So this is a drag force. Drag force means here we have written two terms, minority gas and majority gas. What is the minority gas? Ions and electrons. Majority gas, the neutral air. Why minority? Because as we have said, the plasma is a thinly ionized medium. With respect to your neutral gas, H2, N2, O2, the total concentration, with respect to the total concentration of the neutral gas at ionospheric heights, your electron density or the plasma density is 10 to the power minus 3 or even less. Okay? with respect to the neutral gas. That means if you have 1000 or more neutral gas atoms and molecules, you may have only one electron or one ion. So the ionosphere is a thinly ionized medium, thinly ionized. It has effects on radio propagation, it has effects on the temperature of the thermosphere, etc., etc. That is okay, fine. But the number density of ions and electrons with respect to the neutral gas is very, very low. Very, very low. Okay? 10 to the power 12, if it is a neutral density, then it will be 10 to the power 8 or 10 to the power 7, something like that. So your ions and electrons can be considered as a minority gas, and the neutral atoms and molecules together can be called the majority gas, minority and majority, okay? You know these terms. So what happens then, because we are now bringing in the effect of gravity, so NMVW, so NMVW is equal to minus dP by dH minus NMG. We are bringing in this term, NMG, okay? So mg actually, mg because of gravity. So here P is equal to, from normal gas laws, NKT, D already we know, KT by MV, and HN, the scale height for the minority gas, the ions and electrons, can be KT by Mg. KT by Mg. This is the minority gas. Minority gas. The mass is of the electrons as well as of the ions. We'll come to that. We'll come to that in next few steps. This minority gas M, the mass of this gas is both of ions and electrons. Okay. Similarly, the movement of the plasma contains both ions and electrons. Okay. So this V also will be pushing both the ions and electrons. Similarly, you have the mass also having together is the mass of ions and electrons. So NW, you take this MV, you take this M into V, these two to the right hand side, then it becomes this D is equal to KT by MV. You can do this very simple calculation, and NW becomes equal to minus dN/dH plus N by Hn. So here N, the subscript N signifies that this scale height is only for the ions and electrons. Okay? It is not for the majority gas. Scale height for majority gas will be different because the mass is different. Scale height say at 20 kilometer or 30 kilometer or say 10 kilometer will be definitely different because the mass is different. Temperature is also different. Temperature is also different. So your H for the majority gas, the neutral air, will be always different from the H for the ions and electrons. Okay, mass is different, temperature is also different. Okay, only K remaining constant. Only K remaining constant. Temperature will change at thermospheric heights. The mass is different. So this to signify that or to make it clear, we are putting a subscript here, N, so that we do not confuse this H with the H of the neutral gas. Okay? Scale height of the neutral gas, while you discuss, while that low atmospheric processes have been discussed, definitely you know what is scale height. We have also discussed. So H is KT by mg, but at different heights, it will have different values because of temperature, because of the mass. Okay? Now, differentiating the first equation, dn dt is equal to minus divergence del H. So dn dt is equal to minus del del S Wn. So for Wn or Nw, we put this d dn dh, d dn dh plus n by hn. Okay. So this is your dn dt so far. So far, your continuity equation for the if we are neglecting both Q and beta, or say Q and loss, production and loss, then for divergence or for transport or for motion in the vertical direction, your dn dt becomes equal to del del h d dn by dh plus n by hn. Okay. Now, because the plasma is a charged medium, it is plasma, so you have charged particles. Therefore, an electric field will be set up. Whenever there are charged particles, there will always be an electric field. Okay, so as you know, if you go back, take yourself back to your higher secondary or class 8, 9 textbooks, definitely you will remember that this plus or minus will have an electric field around it. Okay, from the plus point or from the minus point, you will have an electric field going in diverse directions. So that electric field will be there because these are charged particles. So they will set up an electric field. And now we are also talking about gravity. Keep all these things in mind. I am going a little fast, but still, we are talking about gravity, we are talking about vertical movement. So when the vertical movement is taking place, gravity is also acting. And you have within the minority gas two species which are not equal in mass. Okay? Like for neutral gas, we have nitrogen and oxygen near the surface till about 80 or 90 kilometers uniformly distributed. Why? And lighter atoms or lighter molecules to the upper atmosphere or in the upper atmosphere because of the action of gravity, the heavier molecules are bound to near the surface of the Earth. Similarly here, the plasma is floating. The plasma is floating within the environment of say 65 kilometer or say 90 kilometer to 1,000 kilometer or so. That is the plasma, it is floating. But within the plasma, you have this minority gas, where you have a non-uniform distribution of the mass. The positive charges will always have a very high mass compared to the mass of the electron, O plus. If we consider simply O plus, or if we consider NO plus, those charged ions will definitely be heavier compared to the electrons. So because of gravity, they will try to settle downward. That means there will be a charge separation between the ions and electrons because of gravity. Because of gravity, there will be a charge separation between the ions and electrons. So if delta H is the height, so if delta H is the charge separation, the electric field E is equal to N E delta H divided by epsilon naught, the constant, is produced. And there will also be a restoring force if a repulsive force is produced because of the charge separation. These electrons and ions will also try to come together, and therefore a restoring force will also be there. So that restoring force will be E multiplied by E. So this one, E N E square delta H by epsilon naught. Okay. So what will happen because of this restoring force? The charge separation is due to the placement of the ions lower than the electrons. Because of the gravitational pull, the ions, because of their mass, has come down and the electrons are slightly above. So if the charge separation is not very large, but if it is, even if it is small, there is a charge separation, small charge separation, you will have an electric field which is equal to that Ne delta H by that constant. So because of this electric field is set up, so there will be restoring force, and that restoring force is multiplied by E multiplied by E. Okay. Now, because of this restoring force, what will happen? The ions will be lifted upward because this is a restoring force. Gravitation is trying to pull the ions down because of gravity, but this restoring electric field or the electric force will try to pull the ions upward, positive ions. And if the positive ions move upward, electrons, because the charge is coming closer, so electrons will try to come downward. So there will be a movement of the ions and electrons towards each other because of this charge separation. If a charge separation takes place, and that will take place because of the action of gravity, the ions and electrons will be trying to come together. That means they will try to reduce the gap between the ions and electrons. Okay, so this force, this electric force or restoring force, is very large compared to the gravitational force on atomic oxygen ion. If we consider, and at a separation of 10 to the power minus 4 millimeter, this gravitational force is negligible compared to the electric restoring force. The gravitational force, as you know, is already, it is very small on these ions and electrons, or the particles of size of atoms or molecules. So this charge separation is quite large. Electric field will be quite large. Also, it will try to move the ions and electrons closer. Okay. So if you consider a charge separation of 10 to the power minus 4 millimeter, 10 to the power minus 4 millimeter, that means 1 by 10,000 mm, then your electric field balancing the gravitational force is larger than 1 microvolt per meter. 1 microvolt per meter. Okay. In terms of electric field, this is a minute electric field. But it is sufficient to prevent significant separation of electrons from positive ions. That is the point. What I'm trying to say, or what this text tries to say, is because of the action of gravity, the ions and electrons will separate, ions lower and electrons higher. Okay? And once they are separated, an electric field will be generated. An electric field will be generated or set up. You place one positive charge and one negative charge, there will be always an electric field between these two. So that is the case here also. Now here we are not considering only one electron or one ion, a large body of atoms, charge, a large body of electrons. So this electron layer, just consider there is an electron layer and there is an ion layer. This ion layer has come down because of gravity, the electron. So they are separated now. Earlier, when they are produced at the same place or same height. One O dissociated to O plus and E. But once it is produced and before it is recombined, it may be pulled down towards the surface of the earth or lower down. So this electric field, what it does is, it will also set up a restoring force. Restoring force means the ions will be pulled or lifted towards the electrons will be pulled back. So it will try to reduce the charge separation. It will try to reduce the charge separation. So the electric field is sufficient to prevent significant separation of electrons from positive ions. Otherwise, there could have been an electron plasma and a ionic plasma within the ionosphere, but it is not the case. If gravitational force would have been much stronger, then you would have always got, or say you would have got an ion plasma and an electron plasma separated by a sufficient distance. But that is not the case because the restoring force set up by the electric field. And because the electric field or the restoring force produced by the electric field is much larger in magnitude compared to the gravitational force. Okay, so as I had mentioned earlier, that mass m will contain two masses, the mass of the electron and the mass of the ion. Okay, and the mass of the ion is very large. We can consider the mass of the ion to be very large compared to the mass of the electron. So this will be approximately mass of the ion divided by 2. Okay, each particle behaves as though it had a charge plus minus E, because if I consider a particle of positive and negative charge together, positive and negative charge, so the charge will be plus minus E, and your mass will be, the total mass will be m E plus mi divided by 2. So your mi divided by 2. So what happens to your scale height? Scale height, because kT by scale height is your kT by mz, but in this case we replace this m by mi by 2, because there are two spaces. Because this is me plus mi divided by 2, average of the mass of electron and mass of ion. Okay, so you can add also mass of the electron to mass of the ion and divided by 2. That will be approximately equal to mass of the ion divided by 2. Okay, so this is the mean mass of the electron and ion, and so the 2 has come in the denominator. So once the 2 has come in the denominator, mi by 2, it goes up. So 2 kT by miz. So this is equal to 2h. H is your kT by mz. So this is 2h. Okay. Similarly, your diffusion coefficient also, because it contains a mass term, so kT by mv becomes mivi, movement of the ions, and it is 2d. Of course, there is one rider that they should be at the same temperature. The ions and electrons are supposed to be at the same temperature, and they are. Okay. So if not, T is replaced by another term, Te plus Ti, ion temperature and electron temperature divided by 2. So you can get another temperature. Okay. So now what we are getting is, in this equation, dn dt, del h, del p, dn dh plus n by hp. Okay. Okay. Question 38. Del h. So from this equation, if there is a diffusive equilibrium means there is no diffusion, or change in the number density with respect to time is equal to 0. Okay? So then, if dn dt is equal to 0, dn dh, because it is this term, dp dn dh plus n by h pi, you can do this simplification. You will get dn dh is equal to minus n by hp, this one. dn dt is equal to 0. So dn dh is equal to n minus n by hp. So dp is not 0, diffusion coefficient is not 0. So this is 0, this one. Or 1 is equal to minus of the other. So that under thermal diffusion, what happens? N is equal to n naught exponential minus h by hp. Okay? N becomes this n becomes equal to n naught exponential minus h by hp. Okay? So electron density exponentially decreases upward with scale height twice that of neutral gas. This is the catch here, because this dp, diffusion coefficient of the plasma, is twice the diffusion coefficient of the neutral gas. Okay, so your distribution will also be affected by that 2 or modified by 2. Therefore, your electron density, because here in HP also you have, this is twice that of HP is equal to H into 2H. This HP is equal to 2H. DP is equal to 2D. Okay, so your if it is this exponential term here, in exponential term, this decrease will be twice as fast. If I put h here, then there is a decrease. It's an exponential decrease. N is equal to n naught. You consider some value at the maximum, height of maximum, or height of 0. So 0 means the maximum here. So n naught is the height at which you get a maximum, from where exponentially your density will decrease. Minus h by h if it is a normal gas, minus h by hp if it is the electrons or ions. So electron density exponentially decreases upward with a scale height twice that of neutral gas. That means your electron density, rate of decrease of electron density will be twice as that of neutral gas. That means fast, twice as fast. The neutral gas, if it comes down to a minimum from say neutral gas is O. O is maximum around 300 kilometer, and it becomes negligible at a height of 900 kilometer. But your electron density then will be reduced from 300 to 900, 600 kilometer, but it will be twice as fast. So its electron density should be negligible at around 600 kilometer or less than that. So it is if there would have been a board, it would have been much easier to explain. But anyway, you can understand these are simple equations, but the terms. HP is 2H, dP is equal to 2D. So diffusion also will be twice that of your normal gas. Okay, so from this theory of diffusion, we can write this beta. Beta is your loss coefficient. So, or this beta, we know alpha and beta, so loss coefficient. So d by h square can be equated to beta. This equation or this expression can be obtained. You can see Hargreaves' book. It is elaborately shown why this d by h square is equal to beta. Not many, I think a set of 3, 4, or 5 equations in the Hargreaves book, you will see why d by h square becomes equal to beta. That this theory of diffusion gives you that F2 peak will form where d is your diffusion coefficient, h is your normal scale height, beta is the loss coefficient. Okay. Now, if your vertical drift W of ions and electrons due either to wind or electric field, then it is again slightly different. Earlier, we have considered the diffusion only due to the gradient and the effect of gravity, and also the effect of the electric field set up by the charge separation because of gravity. Now, in addition to that, in the ionosphere, we know there will be an wind pushing the plasma from one direction to another. Similarly, an electric field also, it can push the plasma upward or downward. Okay? So, because you have a magnetic field also, so your electric field and magnetic field at cross purposes can have the plasma going up and down, force the plasma up and down. Okay, so the peak will be lifted or lowered because of this wind. This wind, neutral wind, is normally written or by or used by the U is used to denote wind. Similarly, as we know, all of us know that electric field is always denoted by capital E, magnetic field by B or H. So wind is denoted by U. So if there is wind, if we consider that there is some wind blowing from one place to another, and it is always there will always be a wind at thermospheric height, at lower heights also, the neutral wind circulation is there, and therefore because of the wind and electric field E, this plasma efflusion, the peak height of the efflusion, which corresponds to these two values, this value d by h square is equal to beta, will be lifted or lowered by a distance, delta hm w by beta. Just 1 minute, just 1 minute. Okay, so what we see is the peak of the ionosphere. That means the F2 region peak, maybe the peak height, not the peak density. The peak height can be changed, or peak height can be changed by wind flowing from one direction to another, or by the electric field. Okay. we can discuss that in detail, how the wind and the electric field changes or can change the height of the F layer. But for the moment, let us keep in mind that these two processes can force the peak height or force the F layer, peak of the F layer or the whole F layer upward or downward, okay? So the equation of diffusion for the ions and electrons resembles the ordinary diffusion equation, del N del T is equal to D del square N. Okay. Now, from this equation, we may consider or we may consider some simplifications or modifications, okay, to this equation. Considering the processes which are involved, okay. Considering the processes which are involved, we can simplify this process by assuming certain things like the vertical number 1 or A, vertical gradient, scale height approximately 50 kilometer are much greater than the horizontal gradient. I have already told you, horizontal gradient, the scale height is about 1000 kilometer. For vertical gradient, your scale height is 50 kilometer under normal conditions. So that this delta can be replaced by ddh. That is why we are doing this. Earlier equations, we have replaced delta by ddh. So, and to this, add your production term and loss term beta n, because this is only your diffusion. This one, del N del T is equal to D del square N or ddhn. This is your diffusion only. That means the second loss term. But already we have one loss term plus the production term. So this continuity equation will have both Q and loss term beta n. Now drift delta NV, delta we can reduce to ddh nw. Already we know. W is the vertical component of ion drift velocity. Wind is plus minus u, blowing towards the equator. Give drift plus minus u cos I along field lines. Vertical component of this is u cos I sin I. Okay. So actually, when I was telling you about the effect of the winds and electric field, I just neglected that term, the magnetic field, because the plasma is within the magnetic field. Already, I think all of us know the plasma is controlled or by the magnetic environment. So magnetic and electric environment, but it is confined within the Earth's magnetic field. Okay. So what happens when the neutral wind is blowing towards the equator? Towards the equator means from higher latitudes towards the equator. You can visualize. If there is a figure, it would have been much better. I think sometime next we can have some figures or like that. When the neutral wind is coming from higher latitudes to the equator, visualize. Say we consider our India itself. Trivandrum is at the equator, magnetic equator, or Port Blair is at the magnetic equator, and you are here, Dibrugarh, Ahmedabad. All these are higher latitudes compared to Trivandrum or Port Blair. So the wind, neutral wind means the wind which always flows because of the temperature difference. There is always a wind circulation. There are many types of wind circulations, but one is the neutral wind, which blows in the thermosphere and also below the thermosphere. So because of the temperature difference at different latitudes, your equator getting the maximum solar radiation, so becoming hot. The other region, polar region, is cold. So because of this temperature difference, you will have winds flowing from one place to another. So if the wind is towards the equator, that means it is blowing from Dibrugarh or Ahmedabad towards Port Blair or Trivandrum, what will happen? Because the field lines, as I had mentioned in one lecture, that field lines are nearly nearly horizontal at the equator, and then it is kind of circular and reaches or foot of the field lines will reach higher altitudes near the that is determined by the deep angle. Okay, Dibrugarh deep angle is 43 degrees. That means if you have a field line, here, if you can draw the field line here over Dibrugarh, then it will have an angle of 43 degrees with respect to the vertical. Okay, so what is happening? These field lines are slant. They are not exactly vertical, they are not exactly horizontal at any place, either the equator or pole. At the equator, the field lines are horizontal, and at the poles, they are exactly vertical. Okay, pole means the magnetic poles. So besides these 2 points, there will always be an angle to the vertical. Now, here you have the field lines. That means a plane which is about 45 degrees towards the horizon or towards the zenith. Now, the wind is blowing. It finds the plasma somewhere within the field lines. So what will happen? Because the plasma can move only along the field lines, it will push. If you have a plane, then the charged particles or the plasma will be pushed upward along the plane. So the neutral wind flowing from the equator, higher latitudes towards the equator, will push the plasma upward. And the reverse will be the case when the neutral wind flows from your equator towards the higher latitudes or towards the poles. Okay, so you can have this drift. This drift, vertical component of the drift towards the equator, u cos I, and if it is towards the other side, the vertical component will be u cos I sin I. Similarly, eastward electric field produces a vertical drift E cross B, then cos I, okay? The electric field, because there is a magnetic field also, so because B is there now. Now we are considering or talking about the magnetic field also, or field lines. So E and B together will push up or pull down the charged particles depending on the direction of the electric field. Okay. So taking account of height variation of D with respect to H, or that this is the height in the ionosphere, H is the scale height, so D is proportional to exponential H by H. So your DDH will be is proportional to exponential h by h. Okay, so this is because the diffusion coefficient is proportional to exponential h by h. So your diffusion coefficient is modified by this term. Because of the presence of gravity, it is also modified by this term. So n minus, this is your drift, okay, plus q plus beta n. Okay, q is your production term, this is beta n is your loss term, recombination or attachment. This is production due to or ionization. Okay, so all these two, ddh plus 1 by h, ddh plus 1 by 2h n minus ddh nw, this is your diffusion. This is your diffusion because of the vertical drift, this nw, this is vertical drift, and this is this is gravitation, and this is because of the doubling of the diffusion coefficient or diffusion coefficient varying exponentially with height. Okay. Therefore, if we can solve this equation, we will get a peak maximum. Solve this means the maximum will be where del n del t is equal to 0, when there is no change of n with respect to t. So your put 0 here, and if you can solve this equation, we will find, already we have shown that d by h square is equal to beta. M is the subscript which signifies the maximum. So dm is your diffusion coefficient at the maximum. Okay, beta m is your loss or recombination coefficient at the maximum. Peak displaced by vertical drift, if the vertical drift is through delta hm, or the vertical drift can change the peak by delta hm is equal to w by beta m. W is your drift velocity. If w is your drift velocity, then w by beta m will be the amount by which your peak, the F region peak, HMF2 will change. Okay. Now, well below the peak, n is equal to q by beta. Below the peak, n is equal to or approximately equal to q by beta, chemical equilibrium. Above the peak, n is equal to exponential h by 2h, so diffusive equilibrium. Peak electron density, Nm is equal to Qm by beta m by day. At night, it decays with a coefficient beta m as exponential beta m by t. So these are the solutions which we can have from this expression. We are not going into very detail, but we may focus on this particular conclusions, you can say. Features of the solution. If we solve this equation, at the height of the maximum, then you will get dm by h square is equal to beta m. If you have a vertical drift, then the peak will be displaced by this amount, delta hm. Now, if you are considering a height much below the peak height, your electron density is simply q by beta. Okay, this is nearly equal to q by beta. But above the peak height, your electron density is exponentially varying minus h by 2h. Here it is chemical equilibrium. That means below the peak, alpha Chapman. So it is chemical equilibrium, and above the peak, it is beta Chapman, and also it is diffusive equilibrium. Okay, so your electron density will decrease by exponential minus h by 2h. We can have these h different values, it will decrease. So at the peak, you have Nm is equal to Qm by B time, normally by day. So what happens? Your upward drift, you see this. It is written in a very simple way. Upward, downward, raises, lowers, increases, decreases. So upward drift raises Hm. If Hm rises, Nm increases. Okay, so this is what we understand from this solution or from physical process. If the drift raises Hm, height of the maximum, say the maximum height right now over Dibrugarh is 300 kilometer. Hm, maximum height of the F2 peak is 300 kilometer at this point of time. So if it is raised upward, if it is pushed upward, then Nm increases. Why? Because, as we have said, it will be under diffusive equilibrium, and also because your recombination is much less. Recombination, the process of recombination or the rate of recombination of ions and electrons will be less. So Nm increases, number density of Nm will increase. Number density of Nm will increase if your F peak height is pushed upward. That means F2 peak height at 300 kilometer and F2 peak height at 250 kilometer will have different densities. 300 kilometer will have more density than 250 kilometer. Okay, we can have profiles, you can have from measure profiles also, you will see that this happens. Similarly, if the drift is downward, then it will push the Hm below, and as a result, Nm will decrease because Nm is chemical equilibrium, first alpha Chapman, chemical equilibrium. So your ion density will reduce fast if the ionosphere is pulled downward. If the ionosphere moves upward, it will remain in the ionized state for a longer time, so electron density increases. Pull downward, electron density decreases. Okay. Similarly, what happens at night? Same thing, but at night your increase and decrease is not very significant, but the rate at which this increase and decrease in density occurs will be slow. That means the process of recombination will be slower as it goes up. It will be faster as it goes down. Okay. So at very high altitudes, okay. At very high altitudes, diffusion completely dominates the continuity equation. And generally, the solution can be written as A1 or some constant exponential minus z by 2 and A2 exponential minus z. This is diffusive solution. This is flux solution. We are not going into details, but let us just keep in mind that at very high altitudes, diffusion will completely dominate the continuity equation. Production and loss, more than production and loss, the diffusion or diffusive equilibrium will be the primary process. Diffusion will be the primary process which will control your ionization level at very high altitudes. Okay. So then your flux is also there. Then protonospheric. Okay. We can think about, or we can stop our discussion about the F2 region here itself. We're not going into detail. photonosphere is topside ionosphere. So that is another topic. I will come to that briefly, but that is another topic. So within the ionosphere, we have D region, we have E, F1, F2, and F1 and F2, the processes are similar, but F1 not exactly similar, but because F1 is much lower compared to F2, so even if the chemical reactions are similar, because of the number density and also because of the effect of the neutral wind and the electric field, gravity, at higher heights or higher altitudes, diffusion takes over the process of production and loss. The process of production and loss is more relevant at lower heights. More relevant at lower heights. At higher heights, above the F2 peak, that means say 500 kilometers, 600 kilometers, 1000 kilometers, your diffusion is the primary process. Production and loss will be there, but diffusion is the primary process. Okay? So this is about F2. Now, about topside ionosphere, I will just give you, you need not read this. I'm just giving you an idea what the topside ionosphere is. Okay? Topside. Normally, people are using these two terms. I don't know exactly from which year or who started using these words, topside and bottom side. But F peak, you consider the F peak and come down. That is bottom of the ionosphere, and F peak go up. That is the top of the ionosphere. You can go up to the plasma sphere or photonosphere, not plasma sphere. You can go up to the photonosphere. What is photonosphere? That is H plus dominated ionosphere. And while discussing our these profiles, I had mentioned that at some point of time, H plus takes over O plus density. H plus density becomes more than O plus density. So that is the transition height. That is the transition height between O plus and H plus, defined from the transition height between alpha and beta Chapman. That H plus and O plus, because O plus density decreases with height, H plus density increases with height. At some point, say around 600 kilometers, 700 kilometers in height, H plus becomes the dominant ion. So we call it as the protonosphere, not exactly ionosphere. It is the protonosphere because it is a H plus dominant plasma, H plus dominant plasma. Now, earlier, till about 1953, or that means half a century ago, the view was that F2 is the region from where radio frequencies will be reflected back. That is still the case. F2 is the region where you get maximum frequency which will be reflected, and above that the ionosphere will be decreasing exponentially, because these expressions, the expressions which Chapman gave, and also the later on when these diffusion terms and other terms were added, but still it was a exponentially decreasing ionosphere. It was an exponentially decreasing ionosphere. Okay, so it was assumed that the ionosphere will exponentially decrease, or calculated. You can calculate also at what height O plus will become nearly equal to 0. Okay, but whistlers, if you have heard this term whistler is whistle, sound. Whistlers are very extremely low frequency radio waves. extremely low frequency radio waves which are produced during lightning. When lightning occurs, whistles, along with your other radiations, including visible light, you get this extremely low frequency radio waves. That extremely low frequency means from 10 to 30 kilohertz. Kilohertz. That means which is audible. We can hear up to about 20 kilohertz. Okay? So that audible range, that means if you have a very sensitive radio receiver which can detect between say 1 to 30 kilohertz, you will at some point of time during lightning will listen to these whistles. It will be just like listening to a very faint whistle which is generated by the lightning flashes. Okay, so when whistlers were studied, it was found that electron concentration may go or the ionosphere may extend up to 3 or 4 Earth radii. How much is 1 Earth radii? I think all of you know radius of the Earth.
I think they should know what.
Radius of the Earth. ইয়াতে ঘূৰি ফুৰিছো জন্ম ললো ইমান দিনে 20 বছৰ 22 বছৰটো কটালো
6400 kilometers. 6400 kilometers.
6400. Okay, this is not exactly 00. 6,400 or 6,370 kilometers or so. Okay, 6,400 kilometers is the radius of the Earth. Okay, your geostationary satellites are placed normally at 6 Earth radii. Okay, about 36,000 kilometers. Where is your GPS? GPS is about slightly above your 3 Earth radii, 20,000 kilometers. Okay, now these whistlers, when these whistlers were studied, because they are electromagnetic waves or radio waves, so you can have propagation. You can have propagation. So this, from propagation studies across continents, because they are very, very low frequency. And if you have a very strong or very sensitive receiver, only very few people have studied whistlers. But from whistler studies, it has been found that the ionosphere can extend up to 3-4 Earth radii sometimes. That means your exponential ionosphere, given by your theory or given by your understanding of the production and loss mechanism and also divergence mechanisms, are not exactly true in the topside ionosphere. The ionosphere do not exponentially decrease. It will decrease exponentially up to a certain height, say up to 400-500 kilometers, and then it tends to kind of remain nearly same or slightly decreasing. Okay, so that part, after advancement in techniques, was found to be more inhabited by H plus ions. So above the ionosphere, which is supposed to be exponentially decreasing, you have an ionosphere which is different from your exponentially decreasing ionosphere, where the density is more or less decreasing, but not as fast as an exponential decrease. It is slightly decreasing, and so therefore, with height, you may reach a height of 3-4 Earth radii, means your 20,000 kilometers, 30,000 kilometers also at some times. But normally up to 1,500 to 2,000 kilometers, you will always have some significant number of H plus ions. So that is the top side. Okay. Now this top side was also measured by some ionosons. How? Inverted ionosons. You have a ionoson at ground, so it will probe the ionosphere up to the F2 peak from the bottom side. So by the same logic, if you put an ionoson, miniature ionoson, in a satellite, what the Japanese did in a satellite and beam the signal, transmitted signal towards the Earth, then you can measure the distribution of the ionosphere above the F2 peak. Same as you can study the distribution from below the F2 peak with an ionoson on Earth, take a satellite or put an ionoson on a satellite. Of course, that will be much smaller in size, miniature in size, like all satellite instruments, satellite-based instruments. So using that, this ionosphere, the global ionosphere was probed using the topside sounder. That was called topside sounder. And many after these Japanese, the Americans also had some ionosons there. So ISIS 1, ISIS 1, ISIS 1B or something like that, some instruments. Many topside soundings are available, topside profiles are available. So these topside profiles are not similar to the bottom side profiles. That is what I am trying to tell you. The process above the F2 peak, as we have mentioned, is mostly dominated by diffusion, and also because it is largely inhabited by only hydrogen ions, or sorry, hydrogen atoms or molecules, you will have a hydrogen ion dominated atmosphere or ionosphere. So you have your D region, then your E region, F1, F2, and then your protonosphere. So this is the distribution. And this distribution is not same everywhere. It is a kind of parabolic only near the F2 peak. Otherwise, you will have to have different equations or different solutions to fit the distribution. Okay, you can look at any other book or that IRI, International Reference Ionosphere, how that distribution is from the bottom side, that means up from about 90 kilometer to the top side 1000 kilometer or so, that distribution is possible, and you fit different equations, parabolic equation near the F2 peak, then other type of equations at the bottom side, E layer, F1 layer, top side, different. It is like that. So far, we have discussed the Chapman process. Then we have also discussed why the simple Chapman do not give us the ionosphere which we observe today. We also are aware of the other processes in the ionosphere, like the other loss process. If I talk about the continuity equation only, other loss process means the transport process, and in this case we are considering transport only in the vertical direction. Transport in the horizontal direction is also possible during geomagnetic storms and all. Some movement is there. So your medium, this whole ionosphere, that its dynamics is controlled by this production, loss, and transport processes. Okay, and if we want to really simulate means try to find out that density distribution or temperature distribution. If we try to find the temperature distribution, density distribution, your this continuity equation itself is sufficient. But if we try to but to be nearly perfect, you should have this momentum equation, because as we have said, this minor gas and major gas, there will be drag, there will be momentum, there will be drag, and viscosity also, temperature. So if we want to know exactly the whole of the ionosphere, we need to solve or understand all these equations, or all these processes, not equations, all these processes. Continuity equation, the processes which govern the continuity equation, the processes which govern the momentum equations, and the processes which govern the energy balance equations. If we can do all that, you understand the ionosphere fully. Otherwise, it will be a partial understanding. Okay, so for our semester classes, or say even for your this coursework, I think coursework definitely will be slightly more detailed. We can leave our discussion confined to only this, that we know the basic things. We know the basic things. But here we have not considered the momentum equations, we have not considered the energy balance equations. Fine. And next, I think in your syllabus, it is the special features of this low latitude, mid latitude, and high latitude ionosphere. Am I right? In the syllabus, MSc syllabus.
Yes, sir.
Low, middle, and high latitude ionosphere. So that I think we will have a subjective discussion next class on Monday. We will have a subjective discussion. Subjective discussion mean, by subjective discussion, what I mean is we will not go into, because that itself will take another 10, 15 or 20 classes. So because low latitude ionosphere is so diverse, you have to have so many processes, discuss about so many processes. If we go into details, each process will take at least one class. So low, mid, and high latitude, what are the principal characteristics of this? That means if somebody asks that why we define this, or we divide the ionosphere into three defined parts, low, middle, and high, then we should be able to tell, at least we should be able to tell that because of this part of the ionosphere is called low latitude. That means where these processes are relevant, or where these processes occur, which do not occur at the other places. At middle latitudes, we have processes which do not normally occur at in the low latitudes, and high latitude ionosphere is completely different from your middle and low latitudes. So we should be able to at least know that the processes which dominate the ionosphere. That's why these three segments. Otherwise, it could have been a simple ionosphere. But it is not like that. Like your atmosphere also, your atmosphere is not uniform. The polar atmosphere is different from your equatorial atmosphere. Similarly, here also your ionosphere is also defined from high latitude ionosphere is defined from low latitude ionosphere. So I will just try to mention, and if possible, if I get sufficient time within Sunday, I will try to show you some pictures of these processes which create these processes, not exactly the processes which create these processes. And that means we will have a kind of a subjective understanding of the distribution or distinction between these three. Distinction between these three. Okay, so I'm giving you a hint about what we will discuss in our next class. Maybe another 2, 3, or 4 classes will complete.
Okay, sir, thank you.
So I think I can stop here now.
Yes,
Or
sir.
if they have any question or anything
Yes.
like that, we can discuss.
Sir.
Yes.
Okay, yesterday I have mentioned about in high solar flare days, the D region absorbing most of the radio
Mm,
waves, right?
mm,
Okay, those sort absorptions are means in molecular physics we have just studied that it is due to absorption of radio waves primarily take place due to spin reversals of electrons and nuclear spins.
mm.
So my big question is that so why this why only on solar flare days this absorption takes place, because ions are always there, right? So spin reversals might take place at any moment.
Uh,
I'm having a very crude knowledge on radio waves.
no, it's okay. It is okay. We also do not have a vast source of knowledge or vast repository of knowledge on anything. Anyway, uh, what I try to say or what happens during a solar flare is it is a very transient phenomena, and during that period, the energy contained or carried to the Earth's ionosphere by the solar radiations is immensely high. Both these X-rays and this Lyman alpha, all these will have very high intensity. The intensity is very. So normally we have a D region because of hard X-rays, because of this. But if your intensity increases, you have more ion production. You have more ion production. So that is what happens. It is so much of ions or electrons, negative ions and negative electrons are produced that it becomes a kind of a blanketing layer. It kinds of a blanketing layer, and whenever your radio waves, we try to kind of study the ionosphere using an ionoson. The radio wave which we transmit will be absorbed totally, but under normal days, because of the number density increases very fast. Because of the number density, very large amount of negative ions and negative electrons. The process of absorption may be same, but under normal circumstances, even if it absorbs, it allows sufficient amount of or sufficiently strong radio waves to pass and then go to ENF. That's why we get ENF during the daytime. Daytime you have the D region, but we get ENF because the radio wave crosses this. Even if there is a possibility of absorption, that will be less because D region ionization itself is very, very less. But during this process, during the solar flare, the amount of ionization in the D region is extremely large. So, correspondingly, your absorption is also large. Mostly it is absorbed, and that's why it is not a very long term phenomena. We had seen, luckily we had seen for maybe 15 or 30 minutes, full absorption. Full absorption for about 15 or 30 minutes during one solar flare, not all solar flares.
Okay, sir.
Yeah.
Sir, again, once radiations gets absorbed, has to be re-emitted, right? So, my next question is, means after these activities are over, are we getting any sort of signatures of re-emission also somehow?
That I'm not sure, because what happens once this total absorption is over, you will get again the radiation, the radio wave transmitted beyond the D region. You will get again ENF. You will get again ENF. When I discuss these instruments, or also when I discuss these latitudes, low, mid, and high, there I will discuss one phenomenon, that is sporadic E. That E is also something, sometimes it happens, so happens that the E layer becomes so thick that it can, normally say, an E layer can reflect 5 megahertz. Just for example, if ES is present, means sporadic E is present. It is a very thin but very thick layer. Thin in dimension. Thin in dimension, just around 100 kilometer, maybe 1 or 2 kilometer, or maybe 10 kilometer across. Normally E region itself is about 10 to 20 kilometers thick. So that region becomes so dense with ions and electrons that you get, what you get is a blanketing kind of, blanketing means you have a kind of an opaque screen beyond which you cannot see up. So that ES is also something, it is not exactly, from ES there will be reflection, it is not absorption. But in the D region, you may get total absorption. That is the difference. But whether this is giving rise to secondary radiations and all, I am not much aware of, or maybe atomic physicists or atomic scientists will know better.
Okay,
Sir,
sir. Thank you, sir.
in that case, yeah, if the energy states are like vibration or rotational energy states are getting excited, then only it will re-emit. But if what happening here is, it is the radiation is being used up for ionization.
Yes.
Yeah, and then like in thermosphere, because the species are getting excited, atomic oxygen, it is getting excited to some higher energy, electrolytic
Yes.
state. So that will be radiated, and that we have already seen in terms of aurora.
Aurora, or at night you get air glows.
That glow is there,
Yeah,
yes.
yeah.
Those kind of things are there. So generally, no need to, I think, just be in a confusing state of mind.
Yeah.
Whatever I have tasted them in molecular physics, these things, because rotational vibrational states of like carbon monoxide, rotational state for carbon dioxide and water vapor present in the atmosphere. This is the vibrational states mostly. Actually, rotation and vibration, these are interacted. So in that case, what happens is when it interacts with a particular radiation, which is a characteristic wavelength for those particular, like for CO2, it's a 23 near about, there are so many bands actually. For absorption. So at those particular, energy, if a CO2 molecule absorbs, it will get excited to definitely, and we are going to get absorption line at that point, and its vibrational energy states will be to be raised to higher states. Okay, so we cannot define how many states. depending upon how much of energy it is getting interacted. So later on, definitely it is going to, and at what wavelength it will emit. At the same wavelength, which is it absorbing, it will emit also. So it's one point of view of whether we are looking at the absorption band of CO2 or emission lines of CO2. The wavelength should be same because it is characteristic of that particular molecule. So similar for other species as well. কিন্তু যদি আমাৰ এনাৰ্জিখিনি আকৌ হেৰিতে ইউজ হৈ গৈছে লাইক আয়নাইজেশ্যনত ইউজ হৈ গৈছে তেতিয়াহ'লে আমি চাইমালটেনিয়াছলি মানে একে ধৰণৰ হৈ থাকিব লাগে গোটেই ৰিয়েকশ্যনবোৰ কিন্তু এইখিনি এনাৰ্জি আকৌ ইয়াতে ইউজ হ'ব নহয় আয়নাইজিং এনাৰ্জিত যদি ইউজ হৈছে তেতিয়াহ'লে তাৰ ভাইব্ৰেশ্যনেল ষ্টেটৰ ছেম নহ'ব ৱেভলেন্থবোৰ বেলেগ বেলেগ হ'ব আয়নাইজ কৰিবলৈ যিমান এনাৰ্জি লাগে কাৰণ ভাইব্ৰেশ্যনৰ পিছত আকৌ কি হ'ব ডিছ'চিয়েট হ'ব আৰু ইউ নিড মোৰ এনাৰ্জি জাষ্ট ৰোটেশ্যনেলৰ কাৰণে বা ভাইব্ৰেশ্যনেলৰ কাৰণে যিমান লাগে আয়নাইজেশ্যনৰ কাৰণে আৰু বেছি এনাৰ্জি লাগিব চ' ইলেক্ট্ৰমেগনেটিক স্পেক্ট্ৰামটোত তাৰমানে ইট ডিপেণ্ডছ কিমান ৱেভলেন্থত মানে এটা অক্সিজেন এটম বা এটা নাইট্ৰজেন এটম ডিছ'চিয়েট হ'ব ইট ইজ ডেফিনেটলি মোৰ দেন দ্য ভাইব্ৰেশ্যনেল এনাৰ্জি ষ্টেটছ সেইটো কথা আৰু সেই পাৰ্টিকুলাৰ এনাৰ্জিখিনি পালে মানে সেই ডিছ'চিয়েট হ'ব because molecules are getting dissociated into atoms যেটো ৰিয়েলিটিত হয় মানে
right
so
that vibrational and rotational states may not be possible within the ionosphere yes
কাৰণ আমি স্পেচিছ ফৰ আয়নাইজেশ্যনৰ কথা কৈ আছো ন
yes it may not be possible it is for the low atmosphere where you are talking in terms of neutrals isn't it
হেতুৱে কাৰণ হেতু এটমিক অক্সিজেনত ইলেক্ট্ৰনিক ষ্টেটছৰ কথা থাকিব ভাইব্ৰেশ্যনৰ না থাকে
Okay, ma'am. Okay, sir. Thank you.
So, okay then, if no other question.
Okay, sir, তোমালোকৰ কিবা question আছে নেকি?
Regarding from Chapman to whatever we have discussed till today. Any question, if I can answer. Nothing. I think you will need some time to go through the discussions which we had. Maybe possible if I come tomorrow, I will bring those notes with marks and all. Let me see. Let me try today, if possible.
Okay, sir. ঠিক আছে স্যার
Okay then, thank you.
Okay, sir. Thank you, sir.